In this video, we will talk about continuous random variable. Continuous random variable takes all values between an open interval a comma b. For example, age, height, weight, etc. are all continuous random variables. Next, we will see probability density function of a continuous random variable. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. Now we will see what is a probability density function. PDF. Let a function y equals fx be a continuous function without any break whose graph is a continuous curve like this. First, it should be a positive function fx greater than or equal to 0, means for any positive real value the value of this function is positive. Secondly, it is integrable, which means area under the curve of fx and x-axis is finite. If x lies in the closed interval a and b, then number 3, integral fx dx from a to b is 1. Then probability of continuous random variable x, which lies between alpha and beta, where a is less than alpha, alpha is less than beta, and beta is less than b, is given by integral fx dx from alpha to beta. Since the function is positive and the value of integral is 1, shows that the curve of the function is always in the first quadrant. This probability density function and the integral thereof represents area under the curve y equals fx, the x-axis, and the ordinates alpha and beta. So this is the area that represents probability density function PDF. Now we will see how to check a given function y equals fx can be a probability density function. First, the function should be positive and the curve of y equals fx should lie above the x-axis in the first quadrant. And secondly, the total area under the curve and the x-axis is 1, which means integral fx dx from minus infinity to plus infinity is 1. Then the probability that continuous random variable x lies between two numbers alpha and beta is given as probability density function alpha less than or equal to x less than or equal to beta is integral fx dx from alpha to beta. Now suppose integral fx dx from minus infinity to plus infinity is not equal to 1, but integral k times fx dx from minus infinity to plus infinity is equal to 1, then this k is known as normalizing factor, which makes this function y equals fx a probability density function. In the first problem, we have to check whether given function fx is a probability density function. If no, then we have to find the normalizing factor k. Fx is 1 minus x square if 0 is less than x less than 1 and it is 0 otherwise. We also have to find probability when the continuous random variable x is between 0.1 to 0.2 and when x is greater than 0.5. Here, since x lies between 0 and 1, fx is positive or 0 or it is non-negative for all x. Now we find integral fx dx from 0 to 1, which is integral from 0 to 1 of 1 minus x square dx, which is x minus x cube upon 3 from 0 to 1. That will be 1 minus 1 cube is 1 upon 3 minus 0, which will be 3 minus 1, that is 2 upon 3. But since integral fx dx from 0 to 1 is not equal to 1, fx is not a probability density function. Now in order to find the normalizing factor k, we write integral from 0 to 1 of k fx dx equal to 1. That will be k multiplied by the value of this integral from 0 to 1 is 2 upon 3. So k multiplied by 2 upon 3 equals 1. That gives us k equals 3 upon 2. So the normalizing factor k is 3 upon 2. Now this first probability p of 0.1 less than x less than 0.2 will be integral 3.2 into 1 minus x square dx from 0.1 to 0.2, which will be 3 upon 2 into x minus x cube upon 3 from 0.1 to 0.2, which is 3 upon 2. 0.2 minus 0.2 cube upon 3 minus 0.1 minus 0.1 cube upon 3. This works out to be 3 upon 2 into 0.0977, which finally becomes 0.146. So probability of continuous random variable x between 0.1 to 0.2 is 0.146. Next we have to find out probability when the continuous random variable x is greater than 0.5. So for that we write integral from 0.5 to 1 because the maximum probability is 1. Then this normalizing factor 3 upon 2 into function fx 1 minus x square dx. This will be 3 upon 2 x minus x cube upon 3 from 0.5 to 1, which is 3 upon 2. 1 minus 1 cube is 1 upon 3 minus 0.5 minus 0.5 cube upon 3. This finally works out 0.313. So the probability when continuous random variable x is greater than 0.5 is 0.313. And the first probability that we have already found out is 0.146. In the second problem, a continuous random variable x has probability law function fx equals x square 0 less than or equal to x less than or equal to 2. We have to find out whether this function is a probability density function, and if not, then we have to find out the normalizing factor k. And once the function becomes probability density function, we have to find the probability of continuous random variable x when it is between 0.2 and 0.5. And secondly, we have to find the probability when continuous random variable x is greater than or equal to 3, given that x is greater than or equal to half. Now for fx x square to be the probability density function, integral from 0 to 2 fx dx should be 1. So let us evaluate x square dx from 0 to 2. That will be x cube upon 3 from 0 to 2. 2 cube, which is 8 by 3 minus 0. This is not equal to 1, implies that fx equals x square is not a probability density function. So we consider a normalizing factor k and write integral from 0 to 1 of k x square dx equals 1. Value of integral x square dx from 0 to 1 is this 8 upon 3. So it will be k into 8 upon 3 equals 1. That gives k equals 3 upon 8. So 3 upon 8 is the normalizing factor k. Now this first probability is integral 3 upon 8 x square dx from 0.2 to 0.5 will be 3 upon 8 into x cube upon 3 from 0.2 to 0.5, 3 upon 8 into 1 upon 3 into 0.5 cube minus 0.2 cube. This calculation works out 0.0123. So this is the probability 0.0123. Next we have to find probability when x is greater than or equal to 3 upon 4, given that x is greater than or equal to half. This is a conditional probability. So we assume a equals x greater than or equal to 3 upon 4 and b x greater than or equal to half, and we have conditional probability of a when b has occurred equals probability of a intersection b upon probability of b. So let's find out probability of a, which is probability of x greater than or equal to 3 upon 4, which will be 3 upon 8 integral x square dx from 0.75, which is this 3 upon 4, to 2, which is the higher limit of the domain. This will be 3 upon 8 x cube upon 3 from 0.75 to 3, which is PA equals 3 upon 8 into 1 upon 3 into 3 cube, which is 27, minus 0.75 cube, which works out to be 0.947. Next, PB will be probability of x greater than or equal to half, that equals 3 by 8 x square dx from 0.5 to this higher limit 2, which is 3 upon 8 x cube upon 3 from 0.5 to 2, which is 3 by 8 into 1 by 3 into 2 cube is 8 minus 0.5 cube. So PB works out to be 0.984. Now P A intersection B equals PA. So putting these values in this formula, we get probability of A given that B has occurred equals 0.947 upon 0.984, which is 0.96. Next we will study continuous distribution function, which comes into play when we need to know that probability that continuous random variable x is less than a given value of x. This probability is obtained by integrating fx from minus infinity or lower limit of the interval to x, and the function so obtained is called distribution function, denoted by capital Fx. So we have continuous distribution function fx is probability when x is less than or equal to small x, which is given by integral ft dt from minus infinity to x, where random variable x lies between minus infinity to plus infinity. Some characteristics of continuous distribution function fx are: fx is defined for every real number x. Secondly, fx being a probability lies between 0 and 1, which means it is always non-negative. And thirdly, therefore, it is a non-decreasing function. We have seen continuous distribution function f of x to be, from this, derivative of f of x, that is f dash x, which is d by dx of f of x, will be equal to this probability density function fx provided the derivative exists. And fourth, f of x is a continuous distribution function also means probability of continuous random variable x when it lies between a and b is capital F of higher value b minus capital F of lower value a. In the next example, we are given a continuous random variable x having following distribution function fx equals 0 if x is less than or equal to 0, x if x lies between 0 and 1 if x is greater than or equal to 1. From this, we have to find probability density function small fx, and we have to draw the graphs of both probability distribution function capital Fx and probability density function small fx. We have seen that probability density function fx can be obtained by deriving capital Fx, that is f dash x, which will be derivative of 0 0 being constant when x is negative, derivative of x is 1 when x lies between 0 and derivative of constant 1 is 0 when x is greater than 1. First we will draw graph of continuous distribution function capital Fx, which will be for non-positive values it is 0, so the point will be here. Now between 0 and 1 its y equals x, that is identity function. Accordingly the curve will make 45 degrees with the positive x-axis from 0 to this 1 and on x-axis from 0 to 1, and for x greater than or equal to 1 y is continuously 1, so the graph will run horizontal to x-axis. So this is the graph of continuous distribution function capital Fx. Next we draw graph of probability density function small fx. When x is negative, y is 0. When x is between 0 and 1, y is 1. So the graph here will be a horizontal line up to 1, and for x greater than 1 y is 0, which means it will be a vertical line like this. So this is the graph of probability density function small fx. So this is the graph of capital Fx and this is the graph of small fx. In the next problem, we are given a distribution function. From this, we have to find probability density function fx. Also, we have to find probabilities when x is negative, fx is 0, and when x is non-negative, fx is 1 minus e raised to minus x upon 4, which means fx satisfies all the conditions of the distribution function. Corresponding probability density function small fx will be derivative of capital Fx. So f dash x will be derivative of 1 minus e raised to minus x upon 4, which is minus e raised to minus x upon 4 into derivative of minus x upon 4 minus 1 upon 4. So this is when x is non-negative and fx is 0 when x is negative. In order to prove that fx is a probability density function, we have to verify integral fx dx from minus infinity to plus infinity is 1. Therefore, 1/4 integral from 0 to infinity e raised to minus x upon 4 dx will be e raised to minus x upon 4 upon derivative of minus x upon 4 minus 1 upon 4 from 0 to infinity, which will be 1/4 into minus 4 into 1 upon e raised to x upon 4 from 0 to infinity. This will be minus 1 upon e raised to infinity will be 1 upon infinity 0 minus 1 upon e raised to 0 will be 1 upon 1, that is 1. So integral fx dx from 0 to infinity is 1, which proves that this fx is a probability density function fx. It also means that capital Fx is a distribution function. Next we have to find probability when x is less than or equal to 4, where this 4 is lower limit of the interval. So it is f of 4, that is 1 minus e raised to minus 1, 1 minus 1 upon e minus 1 upon e. Next we have to find probability when x is greater than or equal to 8, where this 8 is the higher limit of the interval. Since sum of probabilities from 4 to 8 is 1, probability of x greater than or equal to 8 will be 1 minus probability when x is less than or equal to 8, that is 1 minus f of 8, which is 1 minus, substituting x in here, it will be 1 minus e raised to minus 8 upon 4 minus 2. 1 minus 1 is 0, and this will be minus into minus plus. E raised to minus 2 is 1 upon e square. So this is the probability when x is greater than or equal to 8. Next we find this probability for less than or equal to x less than or equal to 8, which is f8 minus f4. f8 is 1 minus e raised to minus 2, that is 1 upon e square, minus f4 is 1 minus e raised to minus 1, that is 1 minus 1 upon e, which is this 1 minus 1 is 0, minus into minus plus 1 upon e minus this 1 upon e square, which will be e minus 1 upon e square. So this is the probability when x lies between 4 and 8, e minus 1 upon e square. In the next problem, we are given fx equals x into e raised to minus x square upon 2 when x is non-negative and fx is 0 when x is negative. We have to show that fx is a probability density function, and next we have to find distribution function capital Fx. Now for fx to be a probability density function, function should be non-negative when x is non-negative. We have fx equals x e raised to minus x square upon 2 when x is non-negative. This will be x upon e raised to x square upon 2, which is definitely going to be non-negative when x is non-negative. And next, integral fx dx from 0 to infinity should be 1. Here we have x e raised to minus x square upon 2 dx from 0 to infinity. We have to solve this by method of substitution. For that, we will assume this x square upon 2 equals t, that will be x square equals 2t. After differentiation, it will be 2x dx equals 2 dt. 2 upon 2 is 1. We have x dx equals dt. We observe that there is no change in the limits of integration because of this substitution x square equals 2t. So the integral will be, for this x dx we put dt. This e raised to minus x square upon 2 will become e raised to minus t from 0 to infinity. This will be minus e raised to minus t from 0 to infinity, which is minus 1 upon e raised to infinity minus 1 upon e raised to 0. This is 1 upon e raised to infinity is 0, minus 1 upon e raised to 0 is 1, which is 1. So integral fx dx from 0 to infinity is 1, which implies fx is a probability density function. In the next problem, we are given fx equals x into e raised to minus x square upon 2 when x is non-negative and fx is 0 when x is negative. We have to show that fx is a probability density function, and next we have to find distribution function capital Fx. Now for fx to be a probability density function, function should be non-negative when x is non-negative. We have fx equals x e raised to minus x square upon 2 when x is non-negative. This will be x upon e raised to x square upon 2, which is definitely going to be non-negative when x is non-negative. And next, integral fx dx from 0 to infinity should be 1. Here we have x e raised to minus x square upon 2 dx from 0 to infinity. We have to solve this by method of substitution. For that, we will assume this x square upon 2 equals t, that will be x square equals 2t. After differentiation, it will be 2x dx equals 2 dt. 2 upon 2 is 1. We have x dx equals dt. We observe that there is no change in the limits of integration because of this substitution x square equals 2t. So the integral will be, for this x dx we put dt. This e raised to minus x square upon 2 will become e raised to minus t from 0 to infinity. This will be minus e raised to minus t from 0 to infinity, which is minus 1 upon e raised to infinity minus 1 upon e raised to 0. This is 1 upon e raised to infinity is 0 minus 1 upon e raised to 0 is 1, which is 1. So integral fx dx from 0 to infinity is 1, which implies fx is a probability density function, and the distribution function capital Fx is integral fx dx from 0 to x, which is integral x into e raised to minus x square upon 2 dx. As calculated before by method of substitution, this will be minus e raised to minus x square upon 2 from 0 to x, which is minus e raised to minus x square upon 2 minus e raised to 0, that is 1. So finally capital Fx will be 1 minus e raised to minus x square upon 2, where x is non-negative. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel. Make constructive comments to help improve my videos. See you in the next video. Until then, keep watching Number Collage. Thank you.